The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, today's lecture is full of tries and trays and trees. Oh my, lots of different synonyms, all coming from trees. In particular, we're going to cover suffix trees today and various representations of them and how to build them in linear time. They're good things. Some of you may have seen suffix trees before, but hopefully haven't actually seen most of the things I'm going to cover, except for the very basics. So the general problem we're interested in solving today is string matching. And in string matching, we're given two strings. One of them we call the text, T, and the other one we call a pattern, P. So these are both strings over some alphabet. The alphabet we're going to always call capital sigma. Think of that as, it could be binary, 0 and 1, could be ASCII, so there's 256 characters in there, could be Unicode, pick your favorite alphabet. Then it could be ACGT for DNA. And their goal is to find the occurrences of the pattern in the text. And could be we want to find some of those occurrences, or all of them, or count them. And in this lecture, we're only interested in substring searches. So the pattern is just a string. You want to know all the places where P occurs. P might appear multiple times with even overlapping itself. So in those two positions, whatever. You want to find all the shifts of P where it's identical to T. Now there are lots of variations on this problem, which we won't look at in this lecture, such as when the pattern has wildcards in it, or you could imagine it being a regular expression, or you don't want to match exactly, you want to match approximately. It could have some mismatches, or it could require some edits to match T. We're not going to look at those problems. This is both an algorithmic problem and a data structures problem. If I give you this text in the pattern, I just want to know the answer. You can do that in linear time. It's famous Knuth-Morris-Pratt, or Boyer-Moore, or Rabin-Karp. Lots of linear time algorithms for doing that. We're interested in the data structure version of the problem, static data structure. So we're given the text up front, given T, and we want to pre-process T. And then the query consists of the pattern. So we imagine T being very big, P being not so big. And we'd like to spend something like order P time to do a query. That would be ideal, because you have to at least look at the query, and you don't really want to spend time looking at the text. You'd also like something like order T space. We don't want the space of the data structure to be much bigger than the original text. So these are the goals which we will more or less achieve, depending on exactly the problem you want. Sometimes we'll achieve this, sometimes we'll achieve almost this. But this is pretty, these are really nice running times and space. It's all optimal. Before we get to that problem, I want to solve a simpler problem, which is necessary to solve this one. So I'll call it a warm-up. And it's our good friend, the predecessor problem, but now among strings. So let's say we have k strings, k texts, t1 to tk. And now the query is you're given some pattern P, and you want to know where P fits among these strings in lexical order. Okay, so regular predecessor, but now comparison is string comparison. So of course, you could try to solve that using our existing predecessor data structures, but they won't do very well. Even a binary search tree is not going to do well here, because comparing two strings could take a very long time if those strings are long. So we don't want to do that. Instead, we're going to build a trie. Now, tries we've seen in the fast sorting lecture, when W is at least log to the 2 plus epsilon of n. And we use tries in a particular setting there. We're going to use them in their more native setting today a lot. In this setting, it's again, a trie is a rooted tree. The children branches are labeled. And in this case, they're labeled with letters in the alphabet, sigma. So you have a node, and let's say we have the English alphabet, A, B, up to Z. Those are your 26 possible children. Some of them may not exist. They're null pointers. Others may point to actual nodes. Okay, that is a trie in its native setting, which is when the alphabet is something you care about. Now, when we used tries before, our alphabet just represented some digit in some kind of arbitrary representation. The digit was made up of log to the epsilon bits. I mean, we were just using it as a tool. But this is where tries actually come from. They come from trying to retrieve strings out of some database. In this case, we're doing predecessor over strings. This is a practical problem. Like a lot of library search engines, you type in the beginning of the title of a book, and it gives you want to know what is the preceding and succeeding book title of what you query for. So this is something people care about, although really they typically want to solve this problem because it's harder. Okay, so that's a trie. Now, to make this actually work, or what we'd like to do, is represent our strings. So how do we use this structure to represent strings t1 through tk? So we're going to represent those strings in the obvious way, which we've done many times in the past when we were doing integer data structures, as root to leaf paths. Because any root to leaf path is just a sequence of letters, and that's a string. So we'll just throw them in there. Now, to do that, we need to change things a little bit. We're going to add a new letter, which we'll usually represent as a $, to the end of every string. Okay, so I have an example. We're going to do four strings, which are various spellings of Anna and Anne. And say we'd like to throw these into a trie. So they all start with A, so at the root, there's going to be 4 branches corresponding to $, A, E, and N. I'm supposing my alphabet is just A, E, N, because that's all that appears here. But everything will be on the A branch. And then from there, we're going to have, let's see, they all go to N next. So they all follow this branch. Then one of them goes to A. These all go to N afterwards. So we've got $, A we use, E, N we use. And on the A branch, we are done. This corresponds to A, N, A. So that we're finished. And so we imagine there being a $sign at the end of this string. And so we follow the $, child. The others are blank. And this leaf here corresponds to A and A. On the other hand, if we could do A, N, N, there's three options. We could be done, or there could be an A or an E to follow. So if we're done, that would correspond to the $ pointer. So that's going to be a leaf corresponding to this string here. Or could be an A, and then we're done. And then we have a leaf corresponding to Anna, A-N-N-A. Or could be we have an E next, and then we're done. Okay, not very exciting, but that is the tri-representation of ANA, ANN, ANNA, and ANNE. Okay, and you can see there's exactly one leaf per word down here. And furthermore, if you take an in-order traversal of those leaves, you get these strings in order. And typically, if you're going to store a data structure like this, you would store these actual pointers. So once you get to a leaf, you know which word matched. So that's a try. Seems pretty trivial. Trivial? I don't know. But it turns out there's something already pretty interesting about this data structure. So how do you do a predecessor search, right? If I'm searching for something like, I don't know, A-N-E, because I made a typo. Then I follow A, N, and then I follow this E branch here and discover, whoops, there's nothing here. But right at that node, I see, okay, well, my predecessor is going to be the max in this subtree, which happens to be ANA. My successor is going to be the min in this subtree, which happens to be ANN. And so I find what I want. How long does it take me to do that? Well, if I store subtree mins and maxes, then I just have to walk down the tree. That will take order p time to walk down. And then once I'm at a node, I've got to do a predecessor or a successor in the node. Okay, so there are two issues. One is, given a node, how do you know which way to walk down? And then when you're done, how do you do predecessor in a node is the fundamental question. Now, this is something we spent a lot of time doing in, say, fusion trees. That was the big challenge. So this is not really so trivial. How do I represent a node? One way to make it trivial is to assume that the alphabet is constant size, like 2. Then, of course, there's nothing to do. It's a binary try. You look at 0, you look at 1. You can figure out anything you need to do if the alphabet is constant. But things get interesting if you imagine, well, the alphabet's some parameter. We don't know how big it is. It might be substantial. So let's think about how you might represent a try, or the node of a try. So let's call this try node representation. So, any suggestions? What are the obvious ways to represent the node of a try? Nothing fancy. I have 3 obvious answers at least. Array. Good, that was my number 1. Any more? That's, I think, the most obvious. Tree. Good. Do a binary search tree. Or? Hash table. Good. Okay, so for each of them, we have query time and space. Okay, if I use an array, meaning I have, let's say for A through Z, I have a pointer that goes either as null or points to the child. This is going to be really fast, right? Because at a node, if I want to know, I just look at the ith letter in my pattern, P. I say, oh, it's a J, and so I look at the J position, I follow it. You might wonder, how do I do predecessor and successor? Well, this is a static data structure. So for every cell, if it's null, I can store the predecessor and successor in the node. So with no more space. Just this is sigma space per node. And so the amount of space is T sigma, which is not so great. But the query is fast. Query is order p time. Okay, BST. The idea of the BST is instead of having a node that has some pointers, some of which may be absent, let's expand it out into something like this. Actually, I'll use colors This will make life a little bit cleaner in a moment because we're going to modify this approach. So let's say that the pointers you care about are red. Those are the actual letter pointers you want to do. So the idea is to expand out this high degree node into binary nodes. You put appropriate keys in here so you can do a binary search. And then eventually you get down to where you need to go. So this structure has height log sigma. And so the query time is going to be p log sigma. So that goes up a little bit. Not perfect. But the space now becomes linear. So that's an improvement. So ideally, we'd like the best of both of these, like optimal query time, optimal space, linear space. And hash tables achieve that. They give you order p space, order p query, and order t space. Again, the issue is some of these cells are absent, so don't use an array. That's like a direct mapped hash table. Use a hash table. Use hashing. That way you can use linear space per node, however many occupied children there are. What is t here, by the way? T is the sum of the lengths of the ti's, because here we're storing multiple ti's. Or it's the number of nodes in the tree. Which, if your strings happen to have a lot of common prefixes, the number of nodes in the tree could be smaller than that, but not in general. Okay. What's the problem with the hash table? Question?
So for the BST, we're not storing the max into each node. We're just going to find the max by.
Yes, for the BST, we need to store some keys in this node that lets you do binary search. For example, every node could store the max in the left subtree, just within this little tree, though.
Okay, so that's why it's not OT sigma space, because even if every node is.
It is order T. Oh, sorry, I see. Why is it not OT sigma space? Yeah, you're only storing one letter here, so it fits in a single word, okay, and 2 pointers. So every node only takes constant space. So it's only T, order T space, not T sigma. Yep. Other questions? Or answers? There's a problem with hashing. It doesn't actually solve the problem we want to solve. It doesn't solve predecessor. Because hashing mixes up the order of the nodes. This was the problem we had with, what's it called? Signature sort, right? Which hashed, it messed up, it permuted all the things in the nodes. And so you didn't know, in a hash table, you can't solve predecessor. That's what the predecessor problem is for. So I guess you could try to throw a predecessor data structure in here. Actually, I hadn't thought of that before. So we could use Y-fast trees or something. And we would get order T space, and I guess with high probability, this is also with high probability. We get order P log sigma, I guess, because you use Van de Boas. So this is, I'm going to have to call it 3.5, Van de Boas. So that would be another approach. So the hashing will not do predecessor. Okay, it will do exact search, which is still an interesting problem. I give you some strings. I want to know, is this string in your set? But it won't solve the predecessor problem. Okay, so this is an interesting solution to hashing, but not quite what we want. And Van de Boas doesn't quite do what we want either. It improves over the BST approach, but we get another log in there. But it's still not order P. Kind of like order P. Or at least instead of order P times log sigma, I'd kind of like order P plus log sigma, or plus log sigma. And order P plus log sigma is known. So that's what I want to tell you about. And this is normally done with a structure called trays, which is a portmanteau, I guess, of tree and array. Somewhere in there, there's a tree and an array. So it's a bit of an awkward word. Those were developed by Cole, Kopelovitz, and Lewinstein in 2006. So fairly recent innovation. So I have this number 6. Trays achieve order P plus log sigma and order T space. So this is pretty good, and they will do predecessor and successor. Definitely an improvement over the BST. It's open whether you could do order p plus log sigma. At least as far as I can tell, no one has worked on this, and maybe we will work on it today. So that's something to think about, whether you could get the best of all of these worlds for predecessor. There's a lower bound. You need to spend at least log sigma time, because even if your try is a single node, you have the predecessor lower bound, and we know log universe size is the best you can do in this regime. Okay, so that's where we're going. Instead of describing trays, though, I'm going to describe a new way to do it, which has never been seen before in any class or anywhere, because it's brand new. It's developed by Martin Farch Colton, who is, did the LCA and the level ancestor structures that we saw last class. And he just told it to me, and it's really cool, so we're going to cover it. So, simpler way to get this same bound of trays. And the first thing we're going to do is use a weight-balanced BST. And this will achieve p plus log k query and linear space. Okay, k, remember, is the number of strings that we're storing. So it's the number of leaves in the try. So it's not quite as good as p plus log sigma, but it's going to be a warm-up. I'm going to do this, and then we're going to improve it. Okay, so remember weight-balanced trees. We talked about them way back in lecture 3, I believe. There's an issue of what is the weight, and typically you say the weight of a subtree is the number of nodes in the subtree. I'm going to change that slightly and say the weight of a subtree is the number of descendant leaves in the subtree, not the number of nodes. Because it's log k. We really care about the number of leaves down there. There could be long paths here, which we are not so excited about. We really care about how many leaves are down there. So like the weight of this node here is 3. There's 3 leaves below it. Okay, so now it should be, you may recall, weight-balanced BSTs try to make the weight of the left subtree within a constant factor of the weight of the right subtree. Because we're static, we can be even simpler and say, find the optimal partition. So we have all these, so we're thinking about this approach, okay? This idea of expanding a large degree node into some binary tree. We have a choice of what binary tree to use, okay? With 3 nodes, not very many choices. It could be this, or it could be a straight line this way, or a straight line that way. Those are different. And if one of these guys is really heavy, one of these children is really heavy, you want to put it closer to the root. So that's what we're going to do. We're going to, let me draw it this way. As kind of an array. But what this array represents is for a node. So here's my node. It has lots of children. Some of these are heavy. Some of them are lighter than others. Okay, we don't know how they're distributed. But they're ordered. We have to preserve the order. So if I take, what this is supposed to represent is the total number of leaves in this subtree. So the total number of leaves here. And then I'm going to partition this rectangle into groups corresponding to these sizes. Okay, so this is small, medium, small, a little less than medium, big, and then small. So something like that. So these horizontal lengths correspond to the number of leaves in these things, correspond to the weight of my children. So I look at that and I say, well, what I'd really like to do is split this in the middle, which may be here. Say, okay, well then I'll split here. That's pretty close to the middle. And so my left subtree will consist of these guys. My right subtree will consist of these guys, and then I recurse. Over here, I split at the middle. I find the thing that's closest to the middle. Over here, I split at the middle. Find the thing that's closest to the middle. And then this is pretty much determined. So my root node corresponds to this one. It's going to partition here. So over on the right, there's going to be, here's going to be the big tree. And then here is the small tree. So this small tree corresponds to this one. This big tree corresponds to this interval. Then on the left, we've got 4 things we need to store. So these are the red pointers that we had before. And then over on the left, we're going to have a partition, and then there's going to be two guys here. It doesn't really matter how we store them. Something like this. They're, I guess, medium and small. And then over on the left, we also have two guys, so it's going to be, again, something like this. So we've got medium and small. Okay, so you see how that worked. Our main goal was to make this big guy as close to the root as possible. So it was the biggest, and that's basically what happened. This one was really big. And we couldn't quite put it as a child of the root because it appeared in the middle, but we could put it as a grandchild of the root. In general, if you have a super heavy child, it will always become a child or a grandchild of the root. And so in constant number of traversals, you'll get there. Now again, you fill in these nodes with some keys so you can do a binary search. But now the binary search might go faster than log sigma, which is what we had before. And indeed, you can prove that this really works well. So what's the claim? Claim is every two edges you follow, either advance one letter in P. These are the red edges that we want to follow. So if we follow a red edge, then we've made progress to the next node. So this would be following a red edge. Or we reduce the number of candidate TIs by 2/3, or I guess two-thirds of its original value. So we lose a third of the strings. That's what I'd like to claim. And it's not too hard to see this. It's sort of, you have to imagine all of these possible partitions, which is a little bit awkward. The idea is the following. If you take one of these arrays, or this view of all the leaves just laid out on a line, you say, well, it would be really nice if, I'd like to split in half, but that will never happen unless I'm really lucky. So let's think about this 1/3 splitting. If I were able to cut anywhere in here, then in one step, actually, I would achieve this 2/3 reduction. I'd lose a third of the nodes, right? Where's my red? If I end up cutting here, for example, then either I go to the left and I lost almost 2/3 of the nodes, or I go to the right and I at least lost this 1/3 of the nodes, or 1/3 of the leaves, I should say. Okay, so that would be a good situation if I got some cut in here. But it might be there is no possible cut I can make in here because there's a giant child in here that has more than 1/3 of the nodes. It would have to span all the way across here. And so I can't make any cuts. I can only cut between child boundaries. Okay, in that situation, you make this, well, this is when I need to follow two edges, not one. When there's a super big child like that, as we said, it will become a grandchild of the root. So it will be, there's the root, and then here is the giant tree. And then there's going to be the other stuff, here and here. So after I go down either one step or two steps, I will either get here, and now this was, sorry, need more red chalks all over the place. This was a red pointer. This is going to a child. And so if I went there, I'm happy. In two steps, I advanced one letter in P. Or in two steps, I went here, or I went here. And this was a huge amount of the nodes. This was at least a third of the nodes. So again, if I end up here or end up here, I lost 2/3 of the candidate leaves. I lost 1/3 of the candidate leaves, leaving 2/3 of them. Okay, so if this happens, I charge to this order P term, and if the other situation happens, I charge the log K term, because I can only reduce K by a factor of 2/3 order log K times. Okay, so this implies order P plus log K search. So a very simple idea. Just change the way we do BSTs, and we get, in some cases, a better bound, but not in all cases, because maybe log k, p plus log k might be bigger than p times log sigma. I mean, k and sigma are kind of incomparable, so we don't know. But that's where method 5 comes in, which is our good friend from last class, leaf trimming. Indirection. Okay, so we're going to use this idea of finding, we're going to cut below maximally deep nodes with the right number of descendants in them. So we need at least sigma descendant. It could just be descendants or descendant leaves, doesn't actually matter. Okay, let me draw a picture maybe. So we've had, this is pretty much what we did before, except before this magic number was log n that we needed, or half log n or something. Now it's going to be sigma that we need. So the idea is we find these maximally deep nodes, dots, that have at least, I guess there's really multiple things hanging off here in general. Could be several things hanging off. But the total number of descendants of each of these nodes is at least sigma. So what that implies is that the number of these dots, the number of the leaves in the top tree, so up here, number of leaves is at most t over sigma, because we can charge each of these nodes to the sigma descendants in each of them. Okay, so that's good because it says we can use method 1, the simple array method, which is fast but spacious. But if our new size of the trie gets divided by a sigma factor, then this turns out to be linear. So up here we use method 1. Now, got to be a little careful because we can't use method 1 on all the nodes. We can definitely use it on the leaves because there aren't too many leaves. That means we can also use it on the number of branching nodes. Number of branching nodes is also going to be at most t over sigma because it's actually one fewer branching node than there are leaves. So, great. I can use arrays on the leaves. I can use arrays on the branching nodes. I can't use it on the non-branching nodes. Non-branching nodes are nodes with a single descendant and everything else is null. What do I do for those nodes? Not very difficult. I just store that one pointer and I store its label. I guess you could think of that as method 2 in a very trivial case. You see, is this the right label? Yes or no. Okay, so I'll call this is the non-branching nodes. Non-branching top nodes. I will use method 2. So I guess this is really, well, for these guys, I use method 1. For these guys, I use method 1. Okay, so I can afford all this. This will all take order t space. And it will be fast because either I'm using arrays or I really don't have any work to do, and so it doesn't really matter what I do. But except I can't use arrays because they would be too spacious. Okay, so that handles the top. Now the issue is what about these bottom structures? The bottom structures, what do we know? They have to have less than sigma nodes, less than sigma descendants. Also less than sigma leaves. So in other words, in these trees, in these trees, we have k less than sigma. Well, then we can afford to use method 4, because our whole goal was to get k down to sigma in this bound. So in the bottom trees, we use method 4. Okay, method 4 was always linear space, and the issue was we paid p plus log k, but now in here, k is less than sigma in these trees. So that means we get order p plus log sigma query time. Okay, and that's the best we know how to do if we want predecessor at the nodes. So it matches this tray bound in a pretty easy way. Just apply white balance, clean things up a little bit, but only do that at the leaves and everywhere up here, basically, except the non-branching nodes use arrays. So for the most part, arrays, and then at the bottom, you use weight balance. So this is how you ought to represent a trie. If you want to preserve the order of the children, this is the best we know how to do. If you don't want to preserve order, just use a hash table. So it depends on the application. One fun application of this is string sorting. It's not a data structures problem, so I don't want to spend too much time on it, but you use this trie data structure to sort strings. You just throw in a string and then throw in a string. We didn't talk about dynamic tries, but it can be done. And if you throw it, you just sort of find where you fall off and then add the thing. Now you have to maintain all of this funky stuff, but weight balance trees can be made dynamic, and indirection can be made dynamic. So you end up with, in this sort of simple incremental scheme, you end up with t plus k log sigma to sort k strings of total size t with alphabet size sigma. This is good. If I used, for example, merge sort to sort strings, it's going to be very bad. It's going to be something like t times k times log something. I don't really care about the log. T times k is bad. That's because comparing strings could potentially take t time, and then there's k of them. Whereas this is linear. This is the sum of the lengths of the strings. There's this extra little term, but most of the time that's going to be dominated by the length of the strings. So that's a good way to sort strings using tries. All right. Tries by themselves, though, I mean, this is about all there is to say. So let's move on to suffix trees and compressed tries. Now, we actually did compressed tries in the signature sort lecture. Actually, why don't I go over here? So tries, branches were labeled with letters. That's still going to be true for a compressed trie. But as we saw in that lecture, compressed trie, we're going to get rid of the non-branching nodes. So the idea with the compressed trie is very simple. Just contract non-branching paths into a single edge. So this is our example of a trie. We're just going to modify it to make a compressed trie. Namely, here we have a non-branching path. We have to follow an A, then we have to follow an N. There's no point in having this node. We might as well just have a single edge that says AN on it. Okay, so we go from here, from the root, we're going to have an edge that says AN. And in some sense, the key of this child is A. If you're starting up here and you want to know which way should I go, you should only go this way if your first letter is A. After that, your next letter better be N, otherwise you fell off the tree. So that's the compression we're doing. Now here we have, this is a branching node, so that node we keep intact. This is an N, this is an A. But here it's non-branching. So I'll draw this a little bit longer, though in reality it's just a single edge. And again, the key is A, and then you must have a $sign afterwards. Then you reach a leaf, the first leaf. If we follow the N branch, this is branching, so that node is preserved. If I go this way, it's a $sign, and I reach a leaf. If I go this way, it's an A that must be followed by a $sign, so that's a leaf. And if I go this way, it must be an E followed by a $sign, which is a leaf. Okay, and again, these four leaves can point to these places. So that's the compressed trie. Pretty obvious. The nice thing about the compressed trie is the number, here we knew the number of non-branching nodes was at most the number of leaves. Over here, the number of internal nodes is at most the number of leaves. So this structure has order k nodes in total, because we got rid of all the non-branching nodes. I guess except the root. The root might not be branching, but we've got a big O there to cover us. Okay, and all the things we said about representing tries here, you can do the same thing with a compressed trie. I need to write down that 3.5 here. And in fact, these results get better, because before, order t meant the number of nodes in the trie. Now order t will be the number of nodes in the compressed trie, which is actually order k. So life gets really good in this world. I did it in the trie setting because it's just simpler to think about, but really you would always store a compressed trie. There's no point in storing a trie. You can still do the same kinds of searches. Okay, but really compressed tries are warm up for suffix trees. So let's talk about suffix trees. Suffix trees are a compressed trie. So really they should be called suffix tries, and occasionally people will call them suffix tries, but mostly people call them suffix trees, so for consistency I'll call them trees as well. But they are tries. I'm going to introduce some notation here. Okay, with tries we were thinking about lots of different strings. In this case, we're going back to our string matching problem. We have a single text. We want to preprocess that text. But we're going to turn it into multiple strings by looking at all suffixes of the string. So this is Python notation for everything from letter I onwards. And we do that for all I. So that's a lot of strings, and we build the compressed trie over them. That's the idea. And to make it work out, because you remember with tries we had to append $sign to every string, in this case we just have to append $sign to t, and then all suffixes will end with $sign. So that covers us. $sign again is a character not appearing in the alphabet. And that's it. So that's the definition. Let's do an example. Maybe over here. At this point, we're going for this goal of order p query order t space. Suffix trees will be a way to achieve that goal. Okay, let's do my favorite example, which is banana. I had a friend who said, I know how to spell banana, I just don't know when to stop. It's got this nice pattern to it, and a lot of repeated letters and so on. So I'm going to number the characters. He said that when he was like 6, not when he was older. I think it's a little harder when you're writing it on the board, but we all know how to spell banana, I hope. I got it right? It should be 7 letters, including the $sign. Okay, so there they are. So there's a suffix which is the whole string. There's a suffix which is ANA, $sign. There's a suffix which is NANA, $sign. There's a suffix which is ANA, $sign, suffix NA, $sign, A, $sign, and $sign. And empty, I suppose, but we're not going to store that one. Don't need to. Cool. So I'm going to cheat a little bit and look at my figure because takes a little bit of thinking. One of the final challenge of this lecture will be construct this diagram in linear time, but I'm just, for now, going to cheat. Because it's a little tricky to do it and get all the nodes in sorted order. Okay, so that should give it to us, and then the suffixes are, I'll use another color. 6, 5, 3, 1, 0, 4, 2. Cool. So this I claim is the suffix tree of banana. You see the banana substring. Then the next one is $A $. Then the next one is $. Then the next one is $. Next one is $. Next one is $, and then $. Okay, so that's a nice, clean representation of all the suffixes. And you can see if you wanted to search from the middle of the string, suppose I wanted to search for nan, then it's right there. I just do NaN, and then I'm done. This virtual node in the middle here, along the 1/3 of the way down the edge, that represents NaN. And indeed, if you look at the descendant leaf, that corresponds to an occurrence of NaN. If I was going to look for AN, I would do AN, and so I'm halfway down this edge. And then this subtree represents all the occurrences of AN. If you think about it, there's 2 of them. One that starts at position 3, one that starts at position 1. Here's one occurrence of AN. Here's another occurrence of AN. This works even when they're overlapping. If I search for ANA, I would get here. And then these are the 2 occurrences of ANA, and they actually overlap each other. It's this one and this one.